Today we're going to continue our discussion on infinite series by talking about a special type of series called the alternating series, and also talking about some different types of convergence, absolute and conditional convergence. So first we need to figure out what exactly an alternating series is. And our definition is that an alternating series is a series whose terms alternate between positive and negative. So that means that if one term is positive, the next term is negative, and so on. So your alternating series are always going to contain a -1 to an n power, or a -1 to an n plus 1, or a -1 to an n minus 1, something like that, that when we plug in our different values for the series, we're going to get alternating between positive and negative. So why do we even care about alternating series? Well, because there's actually a test for convergence that's specific to alternating series. It's called the alternating series test. And as convergence tests go, the alternating series test is also a fairly simple test to use. So anytime you see that -1 to a power, your first instinct should be, hey, let me try this test that we're about to learn right here, because it's super simple to use in comparison to some of the other tests. So what is the alternating series test? Well, the alternating series test says that if we have an alternating series, which I'm going to call the sum of a -1 to a power times an an, has all of those an positive. If this series satisfies the following two conditions: one, that an plus 1 is going to be less than or equal to an for all n, and two, that the limit as my n approaches infinity of an is 0, then the series converges. So what does this say? This says that if we have an alternating series, so we're going back and forth between positive and negative terms, but my terms also keep getting smaller, it's decreasing, and when I look at the limit of the terms, they eventually approach 0, then the series is going to converge, meaning that the sum is going to be something finite. So anytime you have a -1 to a power for your series, all we have to do to check convergence is make sure it's decreasing, make sure the limit of the an goes to 0, and then you're done. It's already convergent from there. So let's do an example using this new test. So for an example, let's find out if the series, the sum from 1 to infinity of -1 to the n minus 1 over n, let's see if this converges or diverges. Well, we know it's an alternating series because I have that -1 to a power. So all I have to do is check that the rest of the series is decreasing and that the limit goes to 0, and I'll have my answer. So let's first check what this an refers to in our statement of the alternating series test. The an in that statement refers to everything other than that -1 to the power. So in this particular problem, we have a 1 over n. We need to check condition 1, is it going to be decreasing? Is an plus 1 going to be less than or equal to an? Well, let's just find that out. An plus 1 would be 1 over n plus 1. Is that less than or equal to 1 over n? Well, we're plugging in bigger and bigger numbers for n, meaning n plus 1 is larger than n. But when we divide by a larger number, we get a smaller result. So yes, we are decreasing. Condition 2 is the limit as n goes to infinity of that 1 over n equal to 0? Well, yes it is. If I take 1 and I divide by increasingly bigger numbers, I'm going to get a smaller result until we reach 0. So by my alternating series test, this converges. Not so bad, just 2 quick conditions to check, and we find out that this series converges. And it should be noted that this is actually a very special series. It actually has a name of its own. So this -1 to the n minus 1 power over n is called the alternating harmonic series. And we learned a couple of videos ago that the harmonic series, just the sum of 1 over n, diverges. All that's different about this series is having that -1 to a power, and now we have convergence. So that's kind of nice. Anytime you see this alternating harmonic series, you now know it's going to converge, and you're not going to have to check it each and every time. Well, let's do another example trying to do this alternating series test, because right now, it doesn't feel too bad. We had one example where we just tested these 2 conditions, it worked right away, and we're good to go. Does that mean that it's always going to work every time we have an alternating series? No, it does not mean that. And so we're going to have an example here where this test really doesn't help us that much, and we have to rely on our other tests that we've already learned. So here's our next example. Does the series n equals 1 to infinity of -1 to the n times 3 to the n, or sorry, 3n, over 4n minus 1, does this series converge? So your first instinct when looking at this series should be to try to use the alternating series test, because we do have a -1 to a power. And that is a good instinct to have, so let's try doing the alternating series test. So since it's alternating, we're going to try the alternating series test. Unfortunately, there's 2 things that we have to check for the alternating series test. 1, that the limit of the an goes to 0, and 2, that the terms are decreasing. I can tell you right now, when I ignore this little -1 to the n, so I can look at the an term, an is 3n over 4n minus 1, I can tell by looking at this already, if I try to take the limit as n goes to infinity of this 3n over 4n minus 1, I get 3 over 4, which is definitely not 0. So this tells me that second condition of my alternating series test is not satisfied. Now, does that mean that this diverges? No, it does not. This just means we cannot apply the alternating series test. Remember, the alternating series test said that if you have an alternating series and the terms are decreasing and the limit of the terms goes to 0, then you have convergence. Nowhere does it say that if those 2 conditions are not satisfied that you have divergence. We have no idea what the result is when those conditions aren't satisfied. All we know is that we need to try another test to figure out what's going on. Well, something that we can do to figure out what's going on is, well, I would go ahead and try the test for divergence that we learned a couple of videos ago. Remember, the test for divergence says that we should look at the limit as n goes to infinity of the entire term of our sequence or our series that we're trying to sum up. So notice with the alternating series test, I did not include the -1 to the n power when taking the limit. That was due to the statements of the alternating series test. But for the test for divergence, I have to include everything in my sum when I take the limit. So when I take this limit, we know that this is going to go to either positive or negative 3/4, but just going to go back and forth between the two of them. That -1 to the n power is messing everything up. So since this limit does not exist because I'm not going to any particular number, this means that my series diverges. By the test for divergence. So this example here was just to show you that just because a series is alternating does not mean that you can use just the alternating series test and forget everything else. That's the hardest part about figuring out if series converge or diverge is what test do I use, and if the test I choose doesn't work, what do I do from there? And honestly, all you have to do is just keep trying different tests until you actually get a result. So let's do one more example. Does the series sum from 0 to infinity of -1 to the n over n factorial converge? Well, it is alternating because I have that -1 to a power, so let's try the alternating series test. My an for the alternating series test is 1 over n factorial. Remember that in the statement for the alternating series test, we don't include that -1 to the power in these conditions that we need to check. So I need to check for this an, which is 1 over n factorial, if it's decreasing and if the limit goes to 0. So let's check condition 1 first. Is it decreasing? So I want an plus 1 to be less than or equal to an. Well, 1 over n plus 1 factorial is smaller than 1 over n factorial because n plus 1 factorial is a bigger number than n factorial is. So that is satisfied. And also my limit as n goes to infinity of 1 over n factorial, I have 1 divided by larger and larger and larger numbers, so this limit goes to 0. So by my alternating series test, I do have convergence because both of my conditions were satisfied. All right, so that's what you do when you have an alternating series. Always try the alternating series test first, because if the alternating series test works, it's usually super quick. If it doesn't work, well, it didn't take you that long to try it anyway, so you might as well give it a shot. So now we have to talk about something very special called absolute convergence. So absolute convergence says that a series an is called absolutely convergent if the series given by the absolute values of the ANs is convergent. Well, okay, but why would we want to do that? Well, the reason why we would want to do that is because there's actually a theorem that states if you are absolutely convergent, then you are also convergent. So it's perhaps a little easier to show something's absolutely convergent than to just show it's convergent, and then you could use this to figure out if the actual series is convergent or not. So let's do an example of showing absolute convergence. So an example. Show that the series n equals 1 to infinity of negative 1 to the n minus 1 over n squared is absolutely convergent. Well, if we're going to show that this is absolutely convergent, then that means I need to look at the series of the absolute values of these terms. So I'm going to look at the sum from 1 to infinity of the absolute value of negative 1 to the n minus 1 over n squared. Well, the only thing that changes in that absolute value is that instead of having a negative 1 to a power, I'm always just going to have a 1 on the top because the absolute value of 1 is 1 and the absolute value of negative 1 is also 1. So that means that when I look at the absolute value of this series, I get the series 1 over n squared, which just happens to be a p-series. This is a p-series with p equals 2. And the important thing is that it's a p-series with p larger than 1. And so since that p is larger than 1, I know it converges. And so that tells me that my original series was absolutely convergent. So do you think it's always true that if you have a convergent series that it's also going to be absolutely convergent? The answer to that is no. We've actually already seen an example where that's not the case. We are going to show that the alternating harmonic series is convergent, but not absolutely convergent. Well, we already showed that the alternating harmonic series is convergent. That was our first example today. So I'm just going to put down that it is convergent by the alternating series test. We did that earlier in this exact same video. So we know that the alternating harmonic series is convergent, but we need to show it's not absolutely convergent. To do that, let's take a look at what we get when we take absolute values of our terms. So if I take the absolute value of my alternating harmonic series, I have the absolute values of negative 1 to the n minus 1 power over n, and the only thing that changes when I take the absolute value is that I just have a 1 for my numerator and I still have the n on the denominator. Well, the absolute value of my alternating harmonic series is then my regular harmonic series. And we know that that regular harmonic series diverges. So that means that my alternating harmonic series, even though it converges, it is not absolutely convergent. So what do we call a series that converges but doesn't converge absolutely? We call that conditionally convergent. Let me write down that definition for us. A series which is convergent but not absolutely convergent is called conditionally convergent. And let me quick also write down that theorem that I mentioned earlier. The theorem that says if a series is absolutely convergent, then it is convergent. But remember that this theorem only goes one way. We just had an example that showed the other direction does not work. If you are absolutely convergent, then you are convergent. But if you are convergent, that does not mean that you're absolutely convergent. It only works in one direction. Let's do an example. Is the series the sum from 1 to infinity of cosine of n over n squared convergent or divergent? So all that we have to go off of here is just the series definition. There's nothing indicating that we should do any sort of test to figure out if this converges or diverges. But I would like to point out that we know that cosine is not always positive and it's not always negative. It ranges between -1 and 1. Does that mean we can use the alternating series test? No. This series is not alternating. It doesn't go back and forth between positive, negative like that. It's a little more irregular than that. Some of the terms are positive, some of the terms are negative, but it doesn't just strictly alternate. So I cannot use that alternating series test, but it might not hurt to throw absolute values on this guy and make it always positive. Maybe we can show it's absolutely convergent, which would then, by this theorem, show that it's just regular convergent as well. So let's try taking the absolute value. Let's consider the series sum from 1 to infinity, absolute value of cosine of n over n squared. Well, this is equal to the sum from 1 to infinity, the absolute value of cosine n over n squared, because my n squared is already always positive. So now we just have to remember, what do we know about cosine? Well, cosine's always between -1 and 1, so then absolute value of cosine is always going to be less than or equal to 1. So, since the absolute value of cosine over n squared is going to be less than or equal to 1 over n squared, and the sum of 1 over n squared is a convergent p-series, because p is 2, by my comparison test, this means that this series that we had is absolutely convergent, and therefore it's also convergent. So by the comparison test, my series absolute value of cosine n over n squared is convergent. So my original series, which was just cosine of n over n squared, is absolutely convergent and thus convergent. So that's why that theorem is pretty powerful. This series was a lot easier to work with once it was put inside of absolute values. Then we could just use a nice comparison test, just using our properties of cosine and knowing that it's going to be bounded by 1. We were able to compare it to just a nice simple p series without doing a lot of work. All right, so all we have left for today is a new version of our ratio test that we learned the last time. We can use the ratio test to test for absolute convergence instead of just using it for regular convergence. So let me write down the ratio test for absolute convergence, and we'll do an example using that. So the ratio test for absolute convergence says that if the limit as n goes to infinity of the absolute value of an plus 1 over an equals some L, which is less than 1, then the series an is absolutely convergent. Which of course means that it's also just regular convergent. If this limit an plus 1 over an is some L which is bigger than 1, then my series is divergent. And just like our regular ratio test, if that limit happens to be exactly equal to 1, the ratio test tells you absolutely nothing. So really, this isn't any different from the ratio test that we learned last time, other than the fact that we now have absolute value bars in our statements. And our conclusion about convergence is a conclusion about absolute convergence. But other than that, it's the exact same statement from last time, which is kind of nice. So let's finish up with an example where we're going to use this ratio test for absolute convergence. So we're going to test the series, the sum from 1 to infinity of negative 1 to the n times n to the third over 3 to the n for absolute convergence. Well, to test this for absolute convergence, I'm going to use that absolute convergence ratio test. So I'm going to take a limit as n goes to infinity of the absolute value of an plus 1 over an and see what I get. Now notice the terms in my series here, we have a fraction. So when I'm going to be dividing an plus 1 by an, I'm going to go ahead and rewrite it as multiplying by the reciprocal of an, just to make my work look a little nicer. So I have a limit as n approaches infinity of the absolute value. My an plus 1 is what I get when I plug in an n plus 1 for all of my n's. And then I'm going to multiply by the reciprocal of my AN. All inside of absolute values. And now we want to simplify this as much as we possibly can. First, notice that inside the absolute values, the only thing that's going to change is I'm no longer going to have these -1 to the powers. All of that inside of absolute values just becomes a +1. Also, I can cancel out this 3 to the n, leaving just a 3 in the denominator. So I have a limit as n goes to infinity, n plus 1 to the third on top, a 3 on the bottom, and an n to the third on the bottom. And that's all that I have left. And now when I take this limit here, I can compare my coefficients. If I think about distributing all of this n plus 1 to the third, my term with the highest exponent is going to be an n to the third. In the denominator, I also have an n to the third, but its coefficient happens to be 3. So this limit is the ratio of the coefficients, and I get a limit of 1/3. And 1/3 happens to be less than 1, which means, using my ratio test for absolute convergence, I get that this series was absolutely convergent, and that means it's also just convergent as well. All right, so that's about all I have for us today. There's some more talking about series and how they converge or diverge. And we're going to take a little bit of a break from some videos for about a week, because those of you that are in my class right now, you know you have a test coming up. And everybody else, I will see you after that test is over. And we're going to talk about things called power series, which uses all the info we already know about series and just makes it a little bit more complicated. If you have any questions for me, feel free to drop them down below. If you're in my classes currently, feel free to reach out through email or through office hours to ask your questions as well. And I will see everybody next time.